Got a presentation by Rick Thoman. Rick is the climate scientist and services manager for NOAA's National Weather Service Alaska region, where he specializes in Alaska and high-latitude climate monitoring, as well as forecasting in the 2-week to annual timescales. He's worked for the NWS in Alaska since 1988. He'll be discussing this winter's weather. He'll give a brief overview, and then we'll open the floor to questions. Visual aids will be on this monitor, and we'll make sure they're downloadable from the ASSW Press download folders later. For those of you joining us on the webcast, questions may be asked by clicking on the More Event Details link at the top of the page. We have an administrator monitoring that thread here in the briefing room who will ask your questions. Please make sure you identify yourself and your outlet. For those of you in the room with us, please note that we have a microphone for asking questions. If you raise your hand, we'll bring the microphone forward. With that, you can start the presentation. Thank you.
Okay, well, thank you very much. Thanks everybody in the room for coming and everybody online. And so what I'd like to do for you today is just kind of give you an overview of what's happened in Alaska and also the Arctic during this past winter. Of course, it's been in the headlines, quite a remarkable winter. All Alaskans know that this was yet again another very unusual, very mild winter. And so I hope to give you the straight skinny here. Okay, so here's what we're going to talk about. What happened this winter across Alaska and the Arctic? Well, it was exceptionally warm. Much, but not all of Alaska was dry. And really one of the highlights of this winter in Alaska and also the Arctic has been not just that it's been warm, but it's been persistently warm. There's been an almost complete lack of deep cold weather. I'm going to put this in some historical context for you. Some of what we've seen in Alaska is partially consistent with what we expected in a strong El Nino, which is now winding down in the equatorial Pacific, and it's of course also consistent with the long-term trends, and we'll take a look at that. And since I know you were going to ask why, I thought I'd throw in a slide just to outline some why has it been so unusual in Alaska and the Arctic. Okay. Here's a plot from my NOAA colleagues at the National Centers for Environmental Information, and this is a rank in the last 91 winters in these 13 different regions in Alaska. How did this rank in the last 91 winters? Number one, that fire engine red down in southwest Alaska and the northwest Gulf Coast. This was the warmest winter in those regions in the entire 91 years of a record. And then the numbers show you the rest of the state where they ranked. You can see every one of our 13 regions had a top 5 warmest winter, and most places, most regions actually fell in the top 3, from the North Slope right down to Kodiak Island. Southeast Alaska coming in 4th and 5th, and southeast interior only the 5th warmest. Now what's interesting for Alaskans, this is the 3rd winter in a row that's been mild. This was the warmest of the 3 for the entire 3-month December through January period. When we put all these together and look at the state as a whole, this winter came out as number 2. And so just a little bit behind the warmest winter, which was 2000-2001. And I mentioned that deep cold that's been completely lacking. The lowest temperature so far in Alaska from any community or measured by any person is a paltry 47 below Fahrenheit, minus 43 Celsius at Arctic Village right around Christmas. Now that might sound cold, but if that holds up for the rest of the season, and it wouldn't be climatologically extreme for someplace on the North Slope or the Brooks Range to get colder than that in the next few weeks. If this holds up, that would be by far the warmest Alaska minimum temperature for a whole winter. in the last century, the warmest has been 53 below, and there's not no chance, but there is very little chance that any community or person is going to observe a temperature at that level the rest of the season. So this is really a mark of how unusual and how persistent that warmth has been. Of course, it's also been dry over a large chunk of the state, so same kind of plot here from NCEI and the ranks in the last 91 winters. So the dark browns there, the number ones, this is the driest December through January of record for the regions as a whole, for the West Coast and the central interior. And you can see the North Slope and the rest of the interior coming in the top three. But notice I've got that arrow drawn there, and there, if you look hard there, you can see that it's kind of shaded green. The Northwest Gulf Coast, that's be the Kodiak Island and kind of the eastern side of the Kenai Peninsula, western Prince William Sound, was unusually wet. In fact, the 12th wettest in 91 years. Northern Southeast was also significantly wetter than normal. Otherwise, precipitation generally not too far from normal. This is typical. Precipitation, of course, usually shows much more variability than temperatures. In this case, we have a very good explanation for why this. Persistent southeast winds aloft kept bringing storm after storm into the western Gulf Coast. On the windward sides, precipitates out, that crosses the rugged terrain of Alaska. Most of that moisture gets wrung out. So this pattern, not surprising at all, given the predominant weather pattern we've had for months. Now, I mentioned that this persistence a couple of times, and I think this really graphically illustrates it. This is a temperature anomaly index that we keep at the Weather Service, and what this plots, this attempts to assign a rank from +10 to -10 for the entire state on every day. So we use geographically reasonably evenly distributed stations and compute this index. And look at that. The reds there are these days that were, as a statewide average, significantly above normal. In our 90, so what do we have, 92 days of winter this year? 91 days of winter this year, 61 of them fell into that significantly above normal category. Another 28 fell into the near normal, only two days, and back in right around Christmas on the statewide scale fell into the below normal. Of course, if it was a perfectly average winter, you'd expect about 1/3 in each category. Obviously, this is not that. Notice that only one day since before New Year's has even slightly dipped below that dark zero line. Really remarkable consistency. And this is only, I plotted this out to the end of February. If I showed you the version that goes through yesterday, there has not been a single day yet in March that has been below normal. This pattern continues right through today. Those of you with an interest in western Alaska are well aware that sea ice coverage is extremely low. Here's what the analysis looked like on the last day of February. You'll notice a complete lack of ice in Bristol Bay. Extremely unusual. Virtually just very low ice concentrations, even in Upper Cook Inlet. And the main Bering Sea ice edge, the end of February, barely to St. Matthew Island, nowhere close to the Pribilofs. And this is the lowest Bering Sea ice coverage since 2001 for the end of February. Now, it is entirely possible that this year will set the lowest seasonal maximum Bering Sea ice coverage in the satellite era. It's not a done deal yet. The ice could expand south. At this stage, it's be primarily pushed by winds. So that coverage number could go up in the next few weeks. But it's actually got the maximum ice coverage actually has a ways to go to get to 2001. It's entirely possible we could see the lowest annual maximum extent of ice in the Bering Sea since 1979. Now, of course, snow is a big issue, and this has gotten quite a bit of press, of course, with having to modify the start of the Iditarod following last year's move of the start of Iditarod to Fairbanks. So here was the snowpack analysis by the Natural Resources Conservation Service as of March 1st. On the right is the aerial plot, and I'm sorry, on the left is the aerial plot. On the right is actually the point data. And those yellows and greens are kind of the close to normal snowpack. There's actually some blues that would be the somewhat above normal there in parts of the interior. Notice on that aerial map on the left there, though, there's nothing looks terribly dry except for maybe, or not dry, low snow cover, except for that area in central southeast. Well, that's because, of course, there are places with very low snow cover, such as the urban Anchorage area, the lower Mat-Su, and you can see that on the right-hand side, see some of those red dots indicating less than 25% of normal snow cover, and of course some of those, there's no snow cover at all. But aerially, the area with very low snow cover doesn't cover much area, but it is where, of course, a lot of Alaskans live. Now, statewide, of course, we are in a lot better shape than we were last year. The plot you just saw on the left, and then last year's same date on the right. And notice much more of that fire engine red, the very low snowpack last year. So this year, even where most places, even where it's not so good, it's quite a bit better than last year. And this is important as we move into the spring and we start to get fire weather concerns. Certainly, in especially the high population areas that don't have very little or even no snow cover, it's a big concern. But on the statewide scale, we're in better shape than we were last year. So I thought that people would ask. So I threw in some cumulative plots here of snowfall. And I know these are kind of hard to see. They're a little small, but got some highlights down there on the bottom, too. Those of you from Anchorage, you might have to tease your memory to recall that right before Thanksgiving, snowfall was actually running above normal. And then, like everywhere, or most places in Alaska, then the bottom fell out, and there's been very little snow since then. Similarly, in Juneau, running actually near normal right up till New Year's, but it's collapsed since then. Only 2 inches of snow since the New Year in Juneau, the lowest of record for New Year's to now. These plots are actually through Sunday. Nome on the right, snowfall somewhat above normal, but note, unlike other places, there hasn't been this long drought where there's just been no precipitation. There's been at least some since the first of the year. And then Fairbanks on the right-hand side. For those of you from Fairbanks, of course, record snowy September boosted up our totals. Now at low elevations, most or all of that melted off. However, in the Yukon-Tanana uplands above 2,000 feet or so, that snow did not melt and is actually contributing to the snowpack. And that's part of the reason that there were those areas of above normal snowpack on the March 1st analysis. Some of that snow is what fell in late September. Now, of course, Fairbanks has had practically no snow until today. Since before the 1st of December, our couple 3 inches here will boost us up close to that normal line. But overall, still an extremely dry winter and into the spring. So that's kind of what's happened. Now I want to go to put some of this in historical context for you. So from National Centers for Environmental Information, here's a dot for the average temperature for every winter since 1925-26. The reds are significantly warmer than normal. The black dots are near normal, and the blue dots are significantly colder than average here. And I'm using kind of the standard long-term analysis period here. So 1925 to 2000 is the reference period I'm using. So you don't need any sophisticated analysis to see that this is neither a random buckshot or is there a steady trend. You'll notice there from the late 1940s until the mid-1970s, there's only 3 red dots, and there's a whole bunch of blue dots. On the other hand, since the late 1970s, you can count up the number of blue dots there. So the usual way that this tends to get analyzed is, in part because it's simple, is you just throw on this linear regression line, right? And you say that, when we look at the last 91 years of records in Alaska, temperature records for the state as a whole, we see that temperatures are increasing by about 0.4 degrees Fahrenheit per decade. But that doesn't capture any of the things that we can see with our naked eye, the cooler time in the middle part of the 20th century and the significant lack of winter cold since the late 1970s. So we can do other kinds of analysis, and here's one for you. And so this just this splits up this temperature record. It's exactly the same dots, just a different fit of the temperatures, and you can see early part of the 20th century warmer. Then we had this cool period in the mid-20th century. For those that came here during the pipeline era, you got in on some very cold weather. Hadn't always been like that. It was warmer earlier in the 20th century. And you can see what's happened since the mid-1970s. But look at the difference in that trend line now. Instead of 0.4 degrees, 1.4 degrees since that change. Now, I should say, these lines here and these breakpoints where the lines are inflected, these are, I didn't cherry pick these. These are objectively determined by the software. Looking at the entire Arctic, it's been warm. The graphic here from Brian Brettschneider, a postdoc here at UAF, shows you how this winter, December through February, ranks in this data set, which starts in 1948. So 1948, 49, up through this winter, how did the surface air temperature rank compared to all 68 of those winters? And that fire engine red, again, the warmest of record. You can see most of the Arctic basin, warmest of record. Now, it's not, of course, entirely red. You'll notice there over kind of maybe western Chukotka, easternmost Siberia, it actually was quite cold. And also notice that that cold there over the Atlantic Ocean, kind of south of Greenland. But looking at the Arctic basin as a whole, there's a lot of warm colors on there. NASA released their analysis on Saturday, and in their satellite analysis over the Arctic, so NASA uses north of 60 north, this was the warmest winter in the satellite era, again since 1979. NOAA will release their analysis tomorrow, and so that will be something to look forward to. Now, here's a fun analysis. This is put out by the Danish Meteorological Institute, and this is a plot of daily temperatures north of 80 north. So now you're basically looking right at the polar cap. Well, this is kind of ridiculous. Virtually every single day since September, since late September, has been warmer than normal. I mean, it almost dipped down to normal a few days there. That big spike there, just to the right of the 360, that was that event right around New Year's that got a lot of press when a couple of weather stations close to the North Pole for a few hours got above freezing. Well, that was that spike there. But you can see there was a spike, but it is in no sense since then, like in Alaska, since the New Year's, every single day, just versions of heat. So, of course, being the climate guy, I had to say, okay, well, what's going on in the Arctic? We've looked at the trend for Alaska. Now, using that same database that was that map that Brian Brettschneider ginned up for us, here's a plot of the Arctic basin temperatures I used from 70 to 90 north. And again, using objective fit here of the data, and look at that strong inflection there in I have is 1996 there, 1.4 degrees C trend since there, and look what's happened since the mid 2000s. Again, every single winter is significantly warmer than normal. It's not that some winters are warm and some winters are cold. Since the mid 2000s, every winter is significantly warmer than the long-term normal. This year, the warmest, but obviously it follows the pattern. Okay, last slide. Why? Why, Rick, has it been like this? Okay, well, the bottom line is the stars have aligned. Everything came together to produce this extremely warm winter. We had one of, or maybe the strongest El Nino in the past 70 years, maybe the last century. And strong El Ninos do correlate with significantly warmer than average winter temperatures over the eastern two-thirds of Alaska. That does not hold for western Alaska, so Nome, Kotzebue, and also in general the North Slope. During strong El Nino events, those areas do not necessarily trend warm. So over the eastern two-thirds of the mainland as well as southeast, this warm winter is consistent with that. Additionally, we've had this exceptionally warm Gulf of Alaska. Many of you will recall the blob from 3 years ago. Well, the blob is in some sense still there. But the bottom line is in the Gulf of Alaska, sea surface temperatures are amongst the warmest. By one analysis, this year's winter sea surface temperatures in the Gulf, 5th warmest since 1900. Since 1900. What was the warmest? That was way back in 2014-15. And that's very unusual. When we've had these other spikes in Gulf of Alaska temperatures, the following winters have been the sea surface temperatures much cooler. That didn't happen this year. They dropped off a little bit, but not very much at all. Quite different than the past. That very low Bering Sea ice coverage regionally, that's extremely important. That is certainly driving some of the warmth that we've seen in southwest Alaska. The fact that ice is normally there, and now there's not a speck of ice to be found in Bristol Bay. And of course, as we've discussed, the long-term trends contributing to this. For the Arctic as a whole, of course, it also has gotten some press, but like the Bering Sea on the Atlantic side, very low ice coverage. Svalbard, northernmost civilian community in the world, those islands normally surrounded by ice this time of year. Ice has hardly gotten there, dramatically affecting the climate on the Atlantic side, and that's contributing to that warmth in the Arctic. There's been those multiple pulses of warm air from the Atlantic into the high Arctic that's kept those temperatures persistently warm. And then there's also probably some oceanographic help, too, with warm air flowing north on the Atlantic side. Unlike the Pacific side, where you've got a very tight constriction at the Bering Strait, Atlantic is, of course, completely open to water flowing north from there. So that's all I have for you, and I would be very happy to chat, take questions, anything you like.
All right. Thank you, Rick. That was a great presentation. If anyone has questions, we'll hand you the mic.
My name is Betsy Turner-Boger. I'm with the Arctic Research Consortium of the United States, and I'm just personally curious about how the jet stream is correlated to the weather pattern that we've seen here.
So for Alaska in particular, we've had this persistence of winds coming aloft, so at jet stream level, coming out of the south to southeast, so bringing that warm air from lower latitudes north, also moisture. So hence the wet conditions on the windward side of that in that flow, but then that all gets wrung out. But that providing warm air to much of the state. It's harder to make that argument for the North Slope. There's a lot of mountains between the Gulf of Alaska and the North Slope, and a lot of that gets wrung out. And of course, it's a long distance too. So jet flow is doing something different over the North Slope than it is generally over Barrow. But certainly the very persistent southerly winds aloft, a major contributor to what we've seen this winter.
Rick, based on what you've presented here and looking ahead a bit, is there anything, those impossibly wide, big picture generalizations you can tell us about breakup, river flows, flooding, ice jams, and in the fire season here in the interior, and then more broadly around the Arctic and northern Canada, maybe Siberia as well? Or is that impossible per region to generalize on what kind of breakup season we're looking at and what kind of fire season?
Well, as of currently, and we're getting close, more or less every single tool that we have, this would be dynamic climate models, so take the physics and go forward from today, our statistical tools, which are basically look at past relationships. All of those tools point to a warmer than average, significantly warmer than average spring across not just Alaska, but northern Canada as well. Warm springs, of course, are pretty strongly correlated with early breakup. There is a reduced, but not zero, chance of significant ice jam flooding on Alaska's big rivers during warmer than average springs. Given the state of the snowpack, which is in the interior overall pretty near normal, at this point we would probably favor an earlier than average breakup, and so a reduced but not zero chance of significant ice jam flooding. For the fire season, of course, as we move out of the Northern Hemisphere cold season, some of these big-scale climate drivers have less direct influence. So the forecasts become more difficult. That being said, the current consensus is for an increased chance for significantly above normal temperatures, but also at this point, at least over mainland Alaska, an increased chance for significantly above median precipitation. That sounds like maybe that would be good for fire weather, and maybe it will be. But if that precipitation, of course, comes in the form of lots of thunderstorms, recall last June when we had hundreds of fires start in a week because of intense lightning. They produced rain too, but the lightning won out. So at this point, we would have to say we're going to have to watch it for fire season. Certainly, though, if it's going to be warmer than normal, it's going to up our chances.
Matt Miller from KTOO in Juneau, and I was kind of curious, has there been any modeling done yet in case there is the expected murder-suicide of El Nino and the blob later on this spring and summer? What are the prospects for later on this summer and next winter?
So, a couple of parts to your question here. So, we've got above normal sea surface temperatures kind of in a ring from the Bering Sea along the Alaskan coast and the west coast of North America, and then horseshoed back towards Hawaii. That's for those of you that know what this means, that's the classic positive Pacific decadal oscillation pattern. That's what our blob from 3 years ago has morphed into. But the bottom line is warm sea surface temperatures near the coast. Now, different than previous events, we're seeing that warmth from the blob now extends hundreds of meters below the surface. There's a lot of excess heat in the upper ocean across the Northeast Pacific. And that everything else being equal, which it never is, but everything else being equal, that would suggest that it's going to take a long time to significantly cool the Northeast Pacific because we've got this heat reserve. Now, in the tropical Pacific, El Nino is definitely fading out. More often than not, these strong El Ninos are followed the following winter by La Ninas, so cooler than average temperatures in the central equatorial Pacific. And for Alaska, that certainly increases the chances for cold air outbreaks, extended periods of deep cold. Doesn't necessarily mean that that will happen. Remember, this was the second warmest winter of record. The warmest was 2001-2. That was a weak La Nina winter. We see a lot more variability during La Nina winters, but overall, it does up the chances for colder weather. And if it's colder than for most of Alaska, especially near the coast, of course, ups the chances for significant snow.
I'm Shady Grove Oliver with the Arctic Sounder out of Barrow and Kotzebue. And I was just wondering what these recent winters have been doing to the multi-year sea ice up in the Arctic.
So there is certainly a lot less multi-year ice than there was. Last year, you might recall, that we did have some very thick multi-year ice rotate kind of southwestward from off of the Canadian Arctic islands into the Beaufort Sea. And for the first time in years, all of it did not completely melt. A small patch offshore of Deadhorse did persist. I would like to tell you what the state of the current situation is, and I can tell you what the remote sensing seems to indicate that there is much less multi-year ice in the Beaufort Sea now than there was last year. But I'm going to put an asterisk on that. It looks funny. And some of the modeling of sea ice thickness would suggest there should be more multi-year ice in the Beaufort now than we're seeing. So at this stage, I'm going to defer to the remote sensing experts, and they'll sort that out, and then we'll be able to come back and give you the answer. But certainly overall, dramatically less multi-year ice than there was 20 years ago.
Okay, and sort of a follow-up to that. This is Yara Rosen from the Alaska Dispatch News. The trend to less winter ice is not as dramatic as the trend to less, summer fall ice, but the trend to kind of lower maximums. What effect does that have on the Arctic-wide and in Alaska if you have less winter ice, year after year?
That's an interesting question. At least heretofore, kind of whatever the ice cover is in March in the Bering Sea, that's going to be all gone. That none of that is ever going to contribute to what the seasonal sea ice minimum is in September. That always completely melts out. And on the Pacific side, that's likely to remain the case. I'm somewhat hedging here because the Atlantic side, where I am not an expert, may be moving into a different regime. The lack of ice in the Svalbard area this winter is non-trivial, and some of that is pushing up into areas that at least decades ago often persisted ice year-round. So that could be changing quite a bit. Of course, a year like this, where Arctic-wide, we're either going to be the lowest or second lowest winter coverage. Of course, that means you've got a lot more water exposed. As soon as the sun comes out and starts heating that up, instead of that white ice, snow on ice surface, you've got that just dark water, so you're going to start to absorb that heat, and that's that feedback mechanism that's so important in the Arctic and the changes we're seeing. Less ice breeds less ice.
Katia Arevalo, I'm from Spain, from Spanish News Agency EFE, fellow here. So what are going to be the consequences for mid-latitude of what is happening here this winter?
Well, that is that's a contentious, or let me say, that's an area of active research, and I'm going to defer that one to Dr. Jim Overland, who I believe is here. But certainly at this point, I think the science consensus is that changes in the Arctic do affect the mid-latitude. What happens in the Arctic doesn't stay in the Arctic, but when and where those influences are felt in the mid-latitudes, certainly open to research at this point.
I just want to make sure that I understood something that you said right earlier. I think that you mentioned that the North Slope and Northwest Arctic don't necessarily trend warm during El Nino years, and I was wondering why that is.
The El Nino and its effects on the jet stream have the effect of pushing the main storm track eastward from the Bering Sea into the Gulf of Alaska. And in many, or at least enough El Nino winters, that allows more cold air intrusions from Chukotka to make it into western Alaska. That, in general, has not been the case this year. But in past El Nino winters, that storm track has been far enough east to allow some cold air to work into western Alaska.
Are those all the questions we have? Oh.
Hi, so I am Suzanne Goldenberger from The Guardian, and I'm also one of the science fellows. I wanted to just talk a little bit more about the sort of the significance of the sort of ice cover in terms of a marker. We're so attuned to looking at the sort of summer sea ice as an indicator. If it is one of the lowest, if not the lowest on record, what does that tell us about the sort of, you know, consequences of climate change going forward, or what possible future climate impacts going forward? And if you'd like to talk a little bit more about what it might mean for life for people who depend on the ice.
So are you referring specific to the Arctic-wide minimum?
You want to parse it out to like Bering or the other, you know, you did sort of very little about Bering and Svalbard area.
So certainly, again, if we're starting out very low, you know, that gives a jump on the melt season. Now, it is important to note, for instance, the 2012, which is the current summer minima, is the spring of 2012 was not the lowest spring coverage. So it's not a one-to-one relationship there. But certainly, starting out very low, you know, gives you a jump up. But the ultimate what the final number is in September is, of course, going to be determined primarily by the weather during the summer months, starting with this already very low coverage. For the Bering Sea and around Alaska, of course, much more variability. The highest ice coverage in the Bering Sea during the satellite era was way back in 2012. So much more variability. And that makes sense because Bering Sea ice cover is very strongly controlled by what the weather is during the winter months. So if you get persistent northerly winds during December, January, February across the Bering Sea, you're going to have a big ice coverage. Now, that doesn't mean we can also talk about the quality of the ice, and you asked about impacts on peoples of the Arctic and subarctic. And for peoples that make their home in the Arctic, it's not just about how many hundreds of thousands of square kilometers are covered by ice. What's the quality of the ice? If the ice is too thin to haul your whale out on, that's a big impact, even though on those big, nice Arctic maps, oh, look, it's ice covered. But the quality of the ice has a lot to say about what people can do on the ice. So these kind of changes, and also, of course, the changes, there used to be ice, North Slope, September, certainly in October, that's gone. Well, that requires an entire change of subsistence strategies, in economic strategies, in business strategies.
Gabrowski from the University of Alaska Museum of the North. I was wondering, as we have more and more of these abnormal winters, the Arctic is usually a place that takes a little while to get mapped compared to other parts of the world just because of the remote nature. Is there any sort of infrastructure from the Weather Service or NOAA that is going to be going in there as we get more strange winters like this and need more accurate modeling?
Of course, there's lots of interest in gathering more information in the Arctic. Circumpolarly, of course, there's lots of interest. We have the Arctic Observing Summit here right this week, which is, of course, aimed at that gathering of information in the United States. Both NOAA and other federal agencies, of course, working to gather more accurate information. Of course, in the Arctic, especially, but not exclusively, it's, of course, very difficult to do completely automated observations. There's a lot of ways that things can go wrong, and without commercial power in particular, it can be very difficult to do, but we're working it.
Hi, this is Marie. I'm with the University of Alaska Fairbanks. I was looking back at an old Newsminer story in which you're quoted as saying that April 29th of '93 was the earliest green up on record.
Sounds right.
From your visibility in your office on campus. Drove out to Poker Flat yesterday, and everybody on the bus was commenting that we could see a little bit of green up on the hills. Have you noticed anything up on Tanana that you could say was the earliest ever green up happening? I know it's covered with snow this morning, not very helpful.
I would say no. So remember, for green up, what we're looking for is that leaf bud out. Of course, some species of trees, a biologist helped me out, is it aspens? Actually have that chlorophyll in their bark and trunks, and to start that process early in the north. And so maybe that's what folks are saying. I don't think, though, we have bud out yet. That would be fairly amazing.
I had another warm water anomaly El Nino question. You mentioned the increased heat energy down to a lower depth in the Northeast Pacific. Putting that aside, can you explain for the layman how the wind and the ocean circulation patterns generated by El Nino could effectively put a damper on the blob or the warm water anomaly? Because it seems kind of counterintuitive on the surface, two warm water masses, how one could eventually extinguish the other.
So first, the first thing to remember is when we talk about El Nino and these warm ocean temperatures, we're talking about an area along the equator. So when you're laying on the beach in Maui, you're 1,000 miles north of the El Nino area. So there's not a direct connection there. The way that sea surface temperatures in the equatorial Pacific influence mid and high latitude weather is through changes in the location of those giant tropical thunderstorms that spew massive amounts of moisture and momentum into the upper atmosphere. And then that spirals away from the equator, and it affects the jet stream globally. And preferentially during El Ninos, for western North America and the eastern Pacific, of course, we have more of a southerly flow aloft. And that in it, with southerly flow at the surface, that of course pushes warmer water to the north. So how that might cool the Northeast Pacific, get a lot of storminess. Of course, you got a lot of mixing. In a normal year, when the heat is confined to the very uppermost layers of the ocean, you get a lot of mixing. You can bring up cooler water from below. Well, of course, that's still happening now, but the water down below is warmer than it should be, warmer than normal. So that will be brought up, and it will be cooler than the surface water, but not as cool as it would have been otherwise.
Julia Taylor, I'm from UAF Journalism, and I'm curious, when you are looking at statewide and looking at kind of these long-term trends, are there specific policy decisions that you see that could be impacted by the fact that we do see, at this point, over a 40-year trend of higher temperatures, that you think would be important for legislators and people throughout the state to be looking at?
So I will answer this by saying the data is what it is. We work hard to make it as good as possible. Is it perfect? Of course not. We're human, but the data I think speaks for itself. Everybody can look at those plots, and it's pretty clear what they're saying.
Do we have any additional questions?
Okay, thanks everyone. This was a great presentation. If anyone has follow-up questions, they can email them to Marmy and Grimes. Her address is on the main conference media page at ASSW2016.org/news/media. Thank you.